Dr. Hawes. Thank you for your patience. Thank you for joining us today. The floor is yours.
Okay. Phones are not working.
They're not working?
Yeah, sorry.
Bummer. Stuck to a podium.
You can walk around, it's fine.
Walk around without a mic. Okay, thanks very much, Cody. Appreciate being here and appreciate joining yet another SGC. Can you hear me all right? Very good. So I wanted to spend just a few minutes talking about what is today with Orion. And then Rob's going to talk about what is our Lockheed Martin vision of what can be. And so you'll get a capture of both sides of this. And it's a very, very exciting time to be working on Orion, because we have just literally made it to the Space Launch System for our first launch. That would be good. Appreciate your patience. We went through all kinds of challenges getting slides. Okay. Those look familiar. So Rob, a little bit tongue-in-cheek, didn't really expect this title page to last, but none of us ever cut it out. But obviously we are a bow tie and a vest. So that's the way we generally always are. So as I was saying with Orion, we have been in preparations for the Artemis 1 flight. NASA has now announced that they're targeting in February, or they're going to announce that, I should say. We've been told to work towards a launch period that begins in February of next year. But we have just literally been lifted onto the SLS stack this past week. In fact, moved over Monday to the vertical assembly building, and we're lifted up. We're soft mated now. We'll be hard mated over the next few hours, and hopefully we'll actually start into powered on testing on Saturday. So it is a very, very exciting time getting that ship ready for launch. So here's Artemis 1 prior to being encapsulated in the fairings in our facility there in Florida, in the Neil Armstrong ONC facility. The launch abort system that covers the crew module. And then kind of a side-by-side shot of our colleagues in Bremen. In fact, we have received the ESM for Artemis 2. That actually showed up by Antonov cargo plane last Thursday at the Kennedy Space Center. Several of us happened to be out there to greet her to Florida. And so this week we'll actually also start mating the large adapter ring that serves as the interface between the crew module and the service module. So we're actually positioning the two pieces of the service module to be able to be mated. And then we have the crew module for Artemis 2 here side by side. And this is actually, they are now nearly side by side in the ONC with the ESM in what we call the lifting station. The crew module today is actually right next to it in our clean room for welding operations, but we'll move over to this work stand here in another couple of days. So a lot of things going on in Florida. But it doesn't stop there. Artemis 3 is actually, this is earlier in machining, but the same week, last week on Friday, the Artemis 3 pressure vessel, the whole welded crew module, was delivered to Florida as well. So from this point on in the program, we will always have at least 2 Orion spacecraft in flow in our facility in Florida. So again, a very exciting time. So this piece is actually, and if I looked for Artemis 4 pictures, they would really look like this today. This would really be Artemis 4 being machined. We also have, this was our Artemis 3 welding operations in the machined facility. This is the manufacturing of the side hatch panel. It goes from this to a very complex set of mechanisms that drive the side hatch. And then here's our heat shield. So the Artemis 3 heat shield is already in manufacturing. The composite shell has been cured and it's being mounted onto its titanium frame. So a lot of activity going on already with Artemis 3. And actually the Artemis 4 heat shield is starting into its composite lab. So when NASA contracted with Lockheed Martin for the future Orions, they basically contracted for vehicles 3, 4, and 5 at one time. So we've been able to actually procure material and start the development of all 3 of those spacecraft at the same time, staged appropriately, but it allows us to make the commitment to our industry partners for that longer term purchase. And then I'll turn it over to Rob. I want to leave some time for questions, hopefully. And I think that's it, Rob.
So, like you heard, I've been with Lockheed Martin for 137 years. About 10 of those years were on the Orion program working for Mike, guidance and control and flight software. And then for about 2 years, I was on special assignment to Mike, figuring out how we would move Orion from development into production and driving the cost down by 50%. The reason for that, and SLS is going down that path now, is to free up the funding to move on to the next step. So when Orion flies next year, I'm going to be blown away for 2 reasons. First, because just like all of my colleagues from around the world, getting Orion built has been a lot of blood, sweat, and tears. But in addition, it allows us to start talking about what we're going to do when we get to the moon, not just how we're going to get there. We love our rockets a lot. We love our spacecraft a lot. But let's talk about what it is that we're going to do. We're not just going there to go there. We're going there to do science and also to establish a foothold that'll give us the capabilities to then move on to Mars. So I live in the future. I actually thought my credit card was expired the other day, and my wife's like, "What's the problem?" And I said, "It expired in 22." She goes, "What year do you think it is?" So I tend to live in like 24 and 25 mentally. What we need first as a human race when we get to the moon is going to be mobility. You cannot accomplish everything from putting power stations down to hauling cargo around to moving the crew from the lander over to the locations of interest, because regolith moves at 3 kilometers per second as you land. So where we're going to go on the moon will always be physically separated from the landers. So as a consequence, we partnered up with GM a little bit earlier this year, and this isn't a commercial. It's more to say, for all of you, whether you're in school or early career, or heck, late career, or you're in academia or government, in order to be sustainable, I kind of view it as 2 things. First is that cooperation, that collaboration. It's kind of pithy, but I say that we need the skill and the will of everybody to pull this off. It's much bigger than one country, much less one company. So partnering with GM has been a blast because we're both big companies and we have awesome engineering, and that's about it in terms of what we have in common. So we've had a lot of fun working out ConOps with them. We got the same folks that design Hummers and so forth that do their conceptual design started hooking up with us to figure out what these systems should look like as we work through the use cases. So that has been a great deal of fun. I want to share, though, that mobility isn't a dune buggy. The LTV, which is coming out, is one of many use cases. As Luxembourg was talking, what we need to get into is use cases for the moon. As engineers and scientists and technicians, we tend to jump towards the widgets as opposed to what is it that we're trying to accomplish. And so there's 2 things on the moon that are fundamental to us realizing the capabilities both to export stuff back to the Earth. That's the Earth-Moon economy. There's no lunar economy, right? Unless there's a rich alien on the far side, The lunar economy is an Earth-Moon economy. So what is it that we can sell from the moon that Earthlings will buy? And then the second piece is building up the infrastructure so we can go conquer the solar system. So when you think about mobility, there's moving the crew around, there's performing science, there's dragging power cables around, there's planting nuclear power systems, and there's cracking water to get methane, or to get hydrogen. Oh my gosh, I'm a hydrogen hugger. Nothing wrong with methane up through Leo, but after that, wrong tool for the job. Rob's personal opinion, not Lockheed Martin. So cracking water from the moon to create both, drinking water, of course, you don't need to crack it for that, but oxygen to breathe, and then propulsion and propellant. And that moves into the second piece. So that mobility, without mobility, ability to survive the night, global access pole to pole, the ability to go into the permanently shadowed regions, the PSRs, get some ground truth, and then start cracking water in quantity. That's necessary, and it's the next step. But the next step after that is power and propulsion. If you think about any time in human history where we've expanded, you can't do it without the mobility, you can't do it without power. So we're very, very strong on the use of safe and effective use of space nuclear. NASA has been talking about that more and more. This is all high assay, low enriched uranium, which is just a fancy word for less than 20% enriched, which means non-proliferation, but high enough to get sufficient performance. So I'm giving a little bit of a teaser for a talk that Christy Edwards and Tim Sheehan and their team are going to do this IAC about, 4 years ago. We did a Mars base camp design reference mission, if you will, that wasn't Lockheed centric. It was more, here's one way, kind of an existence proof, if you will, of being able to go to Mars in orbit and then down to the surface within a decade. We updated that now for nuclear propulsion simply because we're seeing now that the technologies required for NTP, nuclear thermal propulsion in particular, it's right there. There's a couple of minor miracles. 2700 Kelvin is hot, and 20 Kelvin to 2700 Kelvin over the course of a few milliseconds, tens of milliseconds, and a meter or whatever the diameter or the axial length is. Those are fun mechanical engineering problems, but they're just mechanical engineering. There really is no rocket science. So I won't walk you through this chart other than this is a teaser to come to the technical session and read the paper. Pretty awesome. For us, we strongly believe in redundancy, both dissimilar redundancy as well as using what you've got, and then backup systems for all safety critical activities. So again, this is our concept that isn't Lockheed centric, but rather everyone should see themselves in different aspects of this. And what's important is to make sure we keep firmly in our mind at least one design reference capability, one example or existence proof of how we can get to Mars quickly. Because if you focus too much on optimizing for the moon, you'll get stuck. And we all know we want to accomplish both, not just the one. So mobility, power and propulsion, and then Mars. It's as simple as 1, 2, 3 from that perspective. The final thing I'll say is just to double down in this forum in particular, what you guys do both as the upcoming generation that in the end was able to figure out even how to transfer files. So if we can transfer files, going to the moon it turns out, I think, to be easier. We're going to have to do it together. It's the next generation, it's all the nations, and it's all of both industry, government, and academia working together. And so this is it's a cool commercial type picture that GM put together. But I love it because it's why I do what I do. This picture sums it all up, is looking deep into space with that wonder. And I love the iconic concept of two companies that have never worked together on anything like this, starting to figure out how to provide infrastructure, which then just lowers the barrier of entry and allows all of us to step up and make all this a reality. So a little bit of a teaser for where we're headed at Lockheed. Questions and answers, probably. At least questions. Sure.
Thank you both very much. I'm sure we'll have lots of questions, lots of awesome information and cool new concepts here. Also to ask about. So thank you both very much. Any questions from the audience here?
Yeah, thank you for your talk. How much open issue is the outer space treaty for the NTP plans.
So that's an excellent question. That one of the wonderful aspects of IAC is the ability for all the nations to come and talk through that. At the moment, there's a lot of rules about what we do on the surface of the moon. From the standpoint of orbital operations, it's more clear that systems that can be used can be used. And we're not, trying to figure out when we get to ISRU. By the way, the NTP, the wonderful thing about that is you crack that water, and now you've got propellant, right? You're Earth independent. So who and how we crack that water, who owns it, and who do we charge, and how much can we charge? Those are all juicy things to come. I will point out from a nuclear, it's kind of funny, when I was growing up in the 1800s, we nuclear was it was later than that, so we actually had invented nuclear, but it wasn't popular, right? It wasn't green, and that was because all of that was highly enriched uranium. With the HALEU, less than 20%, because it cannot be turned into weapons, it's therefore it's just safe, and it's high enough above LEU, which is real low. It's tough to get any power out of an LEU system. It's at that sweet spot. So at the moment, we don't see any issues from that from an NTP perspective. When we start talking about fission reactors on the moon for ISRU, that's when we'll have a lot more interesting dialogue about how do we do that as a world, not just a company.
Thank you so much for the presentation. I have a question about you on space. So you're saying you're going through this steering numbers, and how much of it is actually like true serial production? Like, are you evolving the design? Are you updating the models as you learn, or do you like do 5 of the same and just like get it through and then change some later on?
The work that Rob referred to back in trying to get both Lockheed Martin and NASA to transition their framework from design and development to production and operations still has a couple flights worth of change ahead of us. So Artemis 1 without crew, Artemis 2 adds the crew systems, both displays and controls, and the full suite of life support capability. Artemis 3 adds the full docking capability. A couple other mods still hanging out in terms of ESM propulsion on Artemis 4, but smaller scale changes. And then you throw on the fact that we haven't flown yet. So we don't have that flight test data. We have immense amounts of ground test data, but we don't have that flight test data that may tell us what other things may need to be changed. And so in terms of the fundamental systems, we are buying those for Artemis 3, 4, and 5. And we do anticipate, though, that over time with flight experience, we may want to change some things because we'll be able to open up the operational envelope of the spacecraft more and more. But that will be mostly a analysis-driven process. But I still envision that it could drive some flight systems modifications now. I anticipate those would be fairly small, more heaters there than here, and those kinds of changes as we really spend time in the lunar environment. But you look at the bulk of the spacecraft, it's going to stay the same. And ultimately, it's going to be reused. Artemis 3 will become, actually 4 becomes 7, 5 becomes 8. So we will be advancing more and more reuse of those systems as well.
Also, I think we have time for a couple more questions.
Yeah, thank you very much. I find the cooperation with the GM very interesting. I think it's coming a lot since the most industries can be complementary, as you mentioned. Could you mention if you are working on some similar initiatives with other non-space industry partners?
So, yes,
It's your job.
my job, yes. It kind of goes back to what I say over and over, and I sound like I'm just preaching, but it really requires skill and will of everybody. So we've got multiple ones that are pretty fun. One just came out, gosh, yesterday, I think, while I was in an airplane, which is a partnership with NanoRacks and Voyager to build a commercial LEO platform. NASA's been, and in fact, the Senate appropriations in the US was pretty positive for commercial LEO for 2022. Our goal there is not to replace the space station, but to provide a platform that will be like optimized for some of the stuff we want to do. So manufacturing, of course, science, but you can do that at ISS. But when you talk about in-space manufacturing assembly, for example, with high power and lasers for welding and so forth, not doing it at the International Space Station probably makes sense. So NanoRacks and Voyager has been a really cool partnership. We just announced that. I think, like I said, it was in the last 24 hours. Other places, we're talking to power partners here on Earth, in-space mining companies here on Earth, because you don't want to reinvent the wheel. I'll leave you with one thing. We were talking to the mining folks at one point, and we were asking them, how do we move all this stuff from the PSRs out, to where we can work on it? And they said, if you need to work on it, why would you move it first? And in hindsight, that seems obvious, but it wasn't obvious as an aerospace engineer, where you move the work to where you want it to be done, right? So there are some pretty fundamental discussions that you have with folks that have been doing this for literally hundreds of years here on Earth that, again, the best ideas often seem obvious in hindsight.
Awesome. I think we'll turn it over for one online question, then I'll come back. Lots of good questions.
All right, we have a question from an online delegate. Kushi Shaw would like to know, how will the extremely high temperatures be tackled with the compact fusion reactor, and will it affect the size?
Yeah, so and you said fusion, right? Yeah, so fusion, I can't wait. It's always like 6 years out in $600 million. That's like sort of the standard lowest significant bit of how much is left. So our focus at the moment is on fission. And again, not to be confused with RTGs, right, which are just decomposition of plutonium. So on the fission reactor side, uranium-based, those temperatures are real high, and I'll get to fusion in just a second. Those temperatures are real high, and you just need cutting-edge materials. So there's no plasma containment, there's no magnetic field containment, or what have you. On the fusion side, one of the modest miracles, minor miracles that has to occur is how to actually control that. I think what we'll see personally is we're going to move from nuclear thermal propulsion, nuclear fission power, which is real high power, megawatt, let's say, conversion with, in the end, it's like steam engines, right? It's like some weird steampunk. That's why I love NEP. Converting that nuclear power into actual electrons. Once we get through those, we'll be at the point where we can start dealing with those very, very high-powered systems. And you really just have to keep that hot material away from anything physical. So most of the industry says it'll be some kind of a magnetic containment. But I can't wait. Like, if anybody can hurry up and get fusion, we'll update the Mars base camp like that weekend. It would be transformative.
All right, we have time for one more question.
Thank you very much for the nice topic, for the ideas and where it can go. I have a question related to the stairs from 101 to Orion. You're building the next ones already, but they haven't flown yet. How do you handle that risk? Is it a risk you're allowed to take? Is it so well verified that you can just do it, like it's a short form? Is it just because you have the timeline that you do it?
The timelines and the budgets have been set for years in terms of what you can do. Because of those budgets, we also focused on developing and building our flight systems before we had even done all the qualification of those systems. And so we had some learning in our qualification testing, and we'll certainly have learning when we fly. But I really do think that the learning when we fly is going to be mostly what I consider expanding the operational envelope. In my early days in Space Shuttle, that was very much what we learned. The shuttle vehicles, Columbia had been built, Challenger was well on the way. And so there wasn't as much change between those vehicles, but we learned an awful lot that allowed us to fly much more aggressive and challenging missions over time. And that's really where I see the first few flights of Orion being, is that we will really, and in fact, I know that the launch periods are kind of funny. you have either a 42-day mission or a 28-day mission. It's not really variable in terms of going to the DHRO orbit. I'm personally just really hoping for the long mission because that's just more time, more data in the environment. We'll see how it turns out, but I expect some tweaks, but I really do think it's just going to be, we're going to learn that we've been conservative in our analysis and we really can tackle much more challenging missions.
All right, I've been told there's time for one more question, as long as it's very, that's very exciting.
I ran after a few years for my to be amazed at what hardware problems you can fix in software. And that's why we're ultimately model-based. Again, a couple of things like those that we're fully ready to go tweak what we got to tweak. Keeps us flying. Software for no budget.
Hello, thank you very much. And just wanted to ask, because again, you mentioned collaboration about all the series American companies. So you plan to work with people outside of the US, any other space agencies. And at the same time, I also wanted to ask you, in your previous slide, before this one, you had like a concept for what you want to do for Mars. And I see a lot of specific or solution-oriented, let's say, design. Considering that a lot of those things are in low TRL or have not even been constructed, I just don't understand why being so highly detailed right now on that specific time.
Okay, I'll try to go fast. That was not a quick question. So for the first one, yeah, I can't say enough how important it is for us at Lockheed, and I think NASA would agree, to work with international partners. Whoever's got the best capabilities, the ones that we want to work with. So whether that's power or fission or communications systems, mobility, tires, well, we're working with Goodyear. So tires we got covered, but just about everything else on the rovers, we would love to work with both international companies and international agencies, absolutely. With regards, so a lot of folks have said, by the way, it's a sort of double-edged sword. If we put out a concept and it's visionary, then people are like, well, you're just making stuff up and showing pictures. So when we release something from our advanced programs team, it has to close. The design has to close, by which we mean the math has to work. In order to get the math to work, we have to go to a pretty low level of detail. So it's mass of the inflatables and volume, and of course, mass fractions, reasonable size for the nuclear reactor, et cetera, et cetera. So one of the things I say over and over is view this as an existence proof that there is a solution. Now we can just change it, right? And again, that's why we make sure nobody sees it just as a Lockheed solution. Rather, here's something that could work now. We can evolve from it or go do something completely different. But let's stop saying that we can't get to Mars for 20 years because it's patently untrue.
All right, thank you so much. I want to give another round of applause. All right, we are going to turn over to our panel now in just a few minutes. So relax, take it easy. We're going to set up for the next event. Sorry.
Yeah, the pitch